Okay.
And we might need to go to the YouTube page.
No, that I can do it.
Okay.
Right. Then I'll know whether it's actually happening. Yeah, it may be very interesting that there may not be anybody in the clouds. Yeah, it's working.
Can you hear us?
Oh,
That is the real question here. Sorry, 5 viewers.
yeah.
Yeah.
Yeah. There's a huge delay, but otherwise it is working. Yeah, that's not bad. And actually, that part does work. So apparently there are 5 people watching now. Okay.
I think you should.
Okay, no, I just removed the audio show and then okay. Right.
Oh, what did you do? No, you just covered it.
Why did you do that? No, they will be confused.
Oh, yeah. I think
No, we need the artist right there. Let's just leave it. So you can just turn it this way. I mean, right now, when we go there, we'll go there. Otherwise, we can turn it this way. Sure. Oh, you made it go up or something nicely?
Actually, is it possible?
I don't know that, but it is, yeah.
Okay. It's actually like this.
Oh, that's interesting too. Okay, fine. Well, anyways, if there's any questions, we'll answer. Maybe that's bad.
No, you can see.
Okay. There is a huge. Link.
No, 30 seconds. I think
Oh, so she says the sound is bad. Okay, let me, how about this? Okay, can you hear me now? Yeah, this is actually, I can just sit here. That way I can answer the chat.
pretty sure the microphone.
It's fixed now. Okay, great. I am sitting next to the mic. Oh, you can turn it to me so that sure. Oh, it is actually. Yeah.
Should I close the blinds?
No, that's fine. Okay. Yeah, you can keep the door open if there's anybody. I did say by 28, right?
Yeah.
I don't know what. Okay, so that's basically also this is like you must see what's happening. So that's what it's. Okay. Or I can just sit that side. That way, then they won't be talking about. Yeah, I think this is fine. Well, this thing does have pretty interesting. It's interesting that there's like none of the people showed up here. Yeah, well, that's okay. It's not as bad. Do we get a no sheet? Yeah, you can see that. That's the whole reason we got this. Yeah. I know, right? Yeah, basically we just. Oh, I thought there's one more person came because there's like a. um, I would say. No, I can see. Could we go over hill climbing? I'm interested on when we would use it. Okay. Okay, I am going to talk about. Okay. So let's see this question. If I stand here. Oh, here I saw him move and then he disappeared. I didn't know what happened. Okay. Okay, let's see. Is this working? Okay. Yeah, I don't think it. Well, it might show up. I can see it there. Okay. So anyway, so for the hill climbing, the idea is there's a very interesting connection between greedy best first search and on one hand and hill climbing on the other hand. And it is useful to understand why they are. I mean, so basically in the case of hill climbing, you have a single, I mean, you have a candidate solution, candidate node, and you look at the neighborhood. And then pick the best neighbor. And go there. Okay. So in essence, in the case of hill climbing, what you're doing is you're considering the neighbor that is closer to the goal, in terms of, I guess if you are already the goal, if you're at a node, which you're the goal node, then you're done. If not, then you're looking at your neighborhood and then looking for one of the neighbors which have higher, are closer to the goal. In the case of, if you remember, we looked at, for example, 8 pins problem. And in the case of 8 pins problem, we noticed that if it's a goal node, then there won't be any conflicts at all. And otherwise, then you look for the neighbors and see which of the neighbors have the least number of conflicts and assume that's going to be your current node. And then you try to look at the neighborhood of that particular node. Okay, so that's what hill climbing is doing. So hill climbing at any given point of time just remembers the current node and then it loops saying, look at the neighborhood, look for the best fit node and then commit to it and move on. Okay, so the interesting question would be, how does that compare to greedy best first search? If you remember, I mean, actually we didn't do this in the class, but I mentioned it yesterday and it's also in the textbook. In greedy best first search, basically you're
writing f of n to be h of n is cost to goal, right? So it looks almost as if greedy best first search is very similar to the hill climbing, almost similar. The big difference is in the context of greedy best first search, you have a search tree. So you actually have a queue of nodes that you are about to expand, and you're just prioritizing that queue using this f function where f is equal to just h of n instead of g of n plus h of n. Okay. Whereas for the hill climbing, there's actually no queue, no tree. This is why for hill climbing, actually the amount of space taken is O1. It takes O1 space because it just needs the space to remember the current node and nothing else. Okay. But then it also has all sorts of problems. What greedy best first search allows, if you have a tree, so in fact, one of the most interesting things is that if you have a finite space, if you have a finite search tree, okay, if you have a finite search tree, then it turns out that if you're doing greedy best first search, you will actually be able to at least exhaust the space. For example, you can go through the entire tree, and if there's no goal node, and say, then it can just say there's no goal node. Whereas hill climbing will never actually exhaust the space because it could potentially be coming to the same node again and again and again because it's not remembering where it has been. Okay. Once you don't remember where it's been, where you've been, you can keep actually going into cycles. This is why the way to improve hill climbing, for example, involves things like taboo list. Taboo list basically says these are the nodes that we have already visited, and I'm not going to visit them again. And the problem, of course, is if you make the taboo list really big, if it becomes like an entire closed list, then you are going to make sure that you will never again look at a node more than once. But at the same time, that would basically kill the space. Instead of O1, you will now have exponential amount of space being taken. Okay. Other than that, both hill climbing and greedy best first search have the same exact types of problems in terms of optimality. Neither of them are guaranteed optimal solution to the goal node, because neither of them keep track of. So this guy is not keeping track of how far it has traveled, and this guy doesn't actually even know where it has been. Okay, so that's like, so these are connected. The greedy best first search is what is known as still systematic search. Systematic search means it's a search with tree, a search tree. And hill climbing is extremely easy. It's just an iterative search algorithm. It doesn't keep track of the search tree at all. It just keeps track of the current node. And if it's the solution, you're done. If not, then you look at the neighborhood and look for a better node in the neighborhood. Okay. And of course, as I said, both of them can fall, terminate with inoptimal solutions. And the way to make hill climbing sort of go towards more appropriate, more optimal solutions is, for example, doing things like random restart search that we talked about. Okay, so that's basically the difference between hill climbing. That's between hill climbing and greedy best first search. Somebody was asking about simulated annealing. Simulated annealing is a particular way of probabilistically increasing the chance that the hill climbing will find the global minimum, okay, or global maximum. So basically, you can think of the cost of your neighbors to be how close they are to the goal. And if the cost becomes minimum, then that means they're actually at the goal node. Okay. And so the real question would be finding in this cost space, you're finding the global minimum. And that's what hill climbing is trying to do. And the way it does that, what is hill climbing? Actually, another way of thinking of hill climbing is gradient descent. That's what we actually did in the class. Right after hill climbing, I said gradient descent. In the context of continuous functions, you really don't have any hope of doing search with search trees. You have to do search with basically gradient based. And gradient based search always has all the problems that hill climbing search has. Okay. And simulated annealing is a particular way of basically making the probability that the hill climbing will find the global up minimum higher. Okay. So once it finds a minimum, then it won't move, because the problem is the classical hill climbing, the way it does is it looks at its neighbors, and not only does it look for the best neighbor, but it checks to see if the best neighbor is better than itself. If the best neighbor is not better than itself, it says, I'm not going to move anymore. Okay. In some sense, that's how you're essentially trying to look for the optimum in the space of the function. So one way of this is called hill climbing, because if you actually reach the top of the hill, then the way you know that you reach the top of the hill is you look around your neighborhood, and if all the nodes, all the places in the neighborhood are at lower elevation than where you are, then you must be at the top of the hill. Except, of course, it could be the top of the small hill and not the big hill. And that is an issue that you have to deal with. Okay. Any other questions? There is a question on, can I talk about value function and policy function? I sent a recorded 20-minute recorded video of how to compute both value and policy for finite horizon MDPs, which is the only thing you need to know. I suggest that you look at it, because that's basically, again, repeats with numbers what I've already discussed in abstract without numbers. Okay. And in essence, while you are computing the policy, essentially in the finite horizon MDP, there is no real difference between computing the policy and computing the value, because when you are computing the optimal value, in essence, you will wind up figuring out which is the action that you took to get that value, and that is the action that you're supposed to do for that horizon. Again, definitely look at that particular worked out example, and that should make sure that will ensure that you understand what's going on in finite horizon MDPs, which is the only thing you need to know. So I'm going to actually remove this implementing thing. Okay. Yeah. So compute. So how do you find heuristic functions? Okay. There are multiple ways. The one that we talked about a lot in the class is that when basically if you have a problem and you're finding the optimal cost to the goal, okay, that would give you the H star. Okay. If you start abstracting the problem, if you start removing the constraints from the problem, then you get a simpler problem. And sometimes you can solve that simpler problem optimally, much more easily. Okay. To put that all in perspective, consider the 8 puzzle problem. Okay. It's very hard to know, given a actually let's not even consider 8 puzzle. 8 puzzle is hard as well. Think of just a plane with a large number of obstacles. Okay, it's a grid world, and I'm in start. I'm in start state here, and I need to get somewhere like here. Okay. Now the optimal path might involve going like that, and finding that could be costly. Okay. So one idea could be you can just say, I will abstract this problem. What can I do to abstract the problem? I can act as if I can pass through obstacles. Right? So it's like obstacles just went away. If the obstacles went away, now I have a different problem. It's a much simpler problem than the previous problem. Can you solve the shortest path from S to G here? Yes, because here it just would be the straight line distance. Okay. The point is, the optimal path in this abstracted problem is guaranteed to be cheaper than the optimal path in the original problem. In the best case, it may have been the case that you have no actual obstacles hitting this area, and so you still get to travel in some straight line distance. But if there were actually obstacles somewhere around here, then this path is not actually feasible. So the real path would be something like that. That would be costlier than this. And for admissibility, all you care about is this length that you are taking as the cost to the goal is actually underestimating the true cost. Okay, so that's basically what you wind up doing. So to compute heuristics for a problem, you abstract the constraints away from the problem. The more constraints you abstract, the easier the problem is. But then the more constraints you abstract, the actual distance that you compute in the easier problem might be too far away from the true cost, true optimal path. And the farther away you are from H star, the less informed you are. So if you remember, we basically talked about this fact that for every node, you want h of n to be less than or equal to h star of n everywhere, right? Except you want it to be, you are really happy if this distance is not too high. So that means if h of n, if you have, this is where h star is for a particular node, and here is h1 and here is h2, then you think h1 is a better approximation. Okay, so again, in this particular case, actually, if you just ignore all the obstacles, okay, that's one type of an abstraction. The other type of an abstraction is I will act as if the obstacles are there, but I will approximate their shapes. I'll approximate their shapes. So suppose I have an obstacle like this, an obstacle like this, right? I can approximate their shapes by basically, putting the biggest circle that I can inscribe. Okay, so that means now every obstacle looks like a circular obstacle. Okay, now if you think of everything as a circular obstacle, then it turns out that the optimal paths would be in terms of the tangents to those circles. And again, those are easier to compute than the final real optimal path. But that path is likely to be closer to the final path than the one that you computed with everything just disappearing. You see what I'm saying? That's the whole point. Now, having come here, we talked about the class. If you are in the business of circumscribing, why don't we, in the business of putting circles, why don't we circumscribe? Why don't we put the blue circles? That should work too, yeah?
And the obstacles are bigger, which would be
You increase the constraint. So you have to reduce the constraint. So you think there are like two different ways we look at this problem. An irregular shaped obstacle now has become circular, so it's a much simpler equation. So in that sense, you think it's a simpler problem. But when we say make the problem less constrained, that means there should be more feasible paths. When you made the obstacles bigger, then there are fewer paths than before. When you made the obstacles smaller or made them disappear, there are more paths than before. Okay, so that's the other thing. So if I give you, this is as simple as this, if I give you a big set, okay, and you are finding the minimum of this big set. Okay, I'm sorry. What I'm saying is, actually, it's not going to go there. But so it's basically once you abstract the obstacles, when you make the obstacles smaller, then there are more feasible paths, and the cheapest of those paths will still be costlier than the cheapest of the smaller set. Okay, so that's what I was trying to say. So if I have, let's say, a set of numbers, n1 to n100, okay, and if I found the min of these, let's say n min. Okay, now I suppose I just basically, when I constrain the problem, I am cutting down some of the numbers. So imagine I only now have n20, n27, n38, n98. If I take the min of this set, you're guaranteed that this minimum is greater than or equal to this minimum. Right? So that's another way of saying is, if I take the minimum of the class, okay, and then minimum of the entire class, okay, and then I only take the minimum grade of the entire class, and I only then compare it to the minimum grade of just the grad students who happen to be enrolled in the class. Okay, that minimum cannot be less than the minimum of the entire class. It has nothing to do with undergrads being smarter or not smarter. It's just a mathematical reality. I could have said the same thing in terms of undergrads. If I take the minimum of the entire class, and I now take the minimum of just the undergrad students, minimum of undergrad students has to be greater than or equal to the minimum of the entire class. Okay, that's basically what is happening here. When you abstract, you are reducing the constraints, you have more paths. You're taking the minimum of those paths. That minimum cannot be longer than the unabstracted problems minimum. That's how you're getting it basically. Okay, and the more abstraction you do, that means the more feasible paths you make feasible, the weaker the bound is, because the heuristic that you're getting that way is going to be basically saying, so in some sense, if you ignore all the obstacles, then you have straight line distance, and that's typically going to be much farther away from the true cost. Okay. Is there any other questions? Yeah, you can expect anything that happened in the homework, and you can expect anything that is also in the specimen test. That's in terms of what kinds of questions. Just 1 second. Yeah, consistency and admissibility of the heuristic. I can talk about that in a minute. Write that down here so that I get to it. In fact, I just sent a Piazza answer to somebody on that. Okay, is there a question here? Yeah. So you want to see how to do the min-max or something?
It's one part of the expecting is used. The part is you say it is guaranteed to do the action.
Okay, let me look at that later. Okay. I might even be able to just talk to you directly about this question. So consistency versus admissibility. Basically, admissibility just says h of n is less than or equal to h star of n. So that is the heuristic value at any node is less than the true cost of going from that node to the goal node. Okay. Whereas consistency says that if you have an n and you have an n dash, then suppose n dash is the child of n, and you took an action A to go from n to n dash, then the cost you incurred is C n A n dash. Okay, the cost you incurred is C n A n dash, and all it is saying is since all of both n and n dash are trying to get to G somewhere here, so there is an estimate of how far n is from G, that is h of n. Okay, there's an estimate of how far n dash is from G, that is h n dash. And then there is an actual exact cost of going from n to n dash, because n dash is the direct descendant of n, that is C n A n dash. There's a little triangle here. All it's saying is the heuristic should actually act as if it's a distance, and it should follow the triangle rule of inequality. Okay, so all that they're basically saying is h of n is less than or equal to C of n A n dash plus h of n dash. Basically, triangle rule of inequality. Okay, that's consistency. Now, the interesting thing, there are two aspects to it. First, it turns out, even I actually just sent a mail on this, it turns out that you can show that if a heuristic is consistent, it is also admissible. Consistency implies admissibility. Okay. And you do that by induction proof. I just sort of showed the sketch if you're interested, but essentially you should at least know that consistency is a stronger property. The other interesting thing is any heuristic that actually has any kind of a distance semantics is probably already going to be consistent. Okay, so for example, if you made a heuristic such as straight line distance, that would definitely be consistent because straight lines actually follow a triangle of inequality. Okay, so do, for example, the Manhattan distance. Manhattan distance also will follow the triangle of inequality. So most heuristics are already consistent. But sometimes, because you essentially can put any value as the heuristic value of a node, okay, you can, in principle, make a heuristic be highly inconsistent. Okay, and so in that sense, basically, you can have an admissible heuristic that is inconsistent. And I'll tell you one very simple way you can have that situation happen. Okay, let's see. What do? We can basically say, imagine you have a big search tree, and think of this strange thing I'm going to tell you. So there are even levels, there are odd levels. Okay, nodes at even levels of depth and odd levels of depth. Suppose I say, give me any admissible heuristic h of n. Okay, and I will say a new heuristic h cap of n is equal to h of n if n is at even level and 0 otherwise. You see what I'm saying? Would h cap of n be admissible?
Yeah, so it's less than.
It's basically 0. All you're doing is this is already admissible, and I'm just replacing in some places instead of h of n, I'm putting a 0. So it will still be admissible. Okay, but clearly it's locally inconsistent. Okay, so what winds up happening is that you would be at an even node, and you think the distance of going from, so the distance that I took to come to this node is, let's say, 4, and the distance left to go to the goal node is, let's say, 7. So you think the f value of this particular node is 11. And then you get a little child for this node who is in the odd level. Okay, so this is 4, and let's say this is 1, 5. Okay, but then its heuristic value is 0. So it looks as if that this is again, actually, it turns out this is exactly the same point I was making earlier. The minimum of a bigger set cannot be bigger than the minimum of a subset. Okay, so if you consider this guy, any path that goes through this node basically there are more paths going through this node than going through this node and this node. Right? And you're still saying that the total cost of the path that goes through this parent node all the way down is 11, but the same path, if it goes through this guy and the child, suddenly becomes 5. That makes no sense. Right? And it's inconsistent heuristic. So what did we do? We did the path max correction. What path max correction did is it said, let me compute the value, f value of this node, and check, but take the f value of this node to be the max of what it says is its f value and its parent's f value. So in essence, you can't be any better than your parent. You can be worse, because I learned more about actual reality, and so you can be worse. In fact, this path is more constrained, right? Paths that go through this node and must also go through this node. There are fewer such paths than paths that just have to go through this node. That's a bigger set. Okay, so this guy suddenly can't wind up having a lower cost, total cost plan. Because if that was possible, then this thing also must be actually 5. Okay, so that's what you wind up, that's why you wind up doing path max. And when you do path max, you are forcing the heuristic to be locally consistent. A more interesting question, actually, again, I talked about this at last, I don't know how much we would have gone through at that time, but since you're talking about it now, is, but you don't actually talk about G values ever being inconsistent. Because G values are, they have physical significance for the problem. They are actual action costs. Unless actions start having negative values, G values don't start reducing as you go to more and more nodes. But H values are just making, you're just making up H value for each node without caring about any other node. And all that you care about admissibility is H value of that node is less than the H star value of that node. So that's exactly what I exploited here. I'm making, I'm following your rule, except for some nodes, I'm actually giving a reasonable value. In fact, the interesting thing is I could have, instead of H, I could have started with H star. And it will still be the same. Okay, I had a perfect heuristic, which is obviously admissible, and then I made this perfect heuristic into a useless heuristic, at least locally, by saying all the even level nodes will get the perfect heuristic value, all the odd level nodes will get 0, as if there is no heuristic at all. Okay, and if such a thing happens, and sometimes it can happen, in fact, nicely, textbook actually points out that when you come up with heuristics, normally you would be hard, you typically tend to think of heuristics as distances in some abstract space, as I mentioned earlier. And in such cases, they will all be consistent because they're actually distance measures. But really nothing about the theory of admissible heuristics requires that the heuristic be so formulated. You could just make up any numbers as long as you're sure that those numbers are less than H star. Since you are allowing that by definition, there is this issue of inconsistency that you have to worry about. But most of the time, you don't care about. The area, yeah, heuristic that is admissible obviously is not automatically consistent. That's exactly what we just said. There's a question on, can we talk about how to compute the optimal action as against value? I'm not quite sure what the context is. In the context of finite horizon MDPs, which is the only thing that you really do care about for this particular test, really you are, so I think the question that you're asking is, can you avoid thinking in terms of values and just going for actions? Maybe you are thinking of the reinforcement learning discussions that we had, but those are quite different. I can go into the details, but as far as you're concerned for tomorrow's test, if you understand finite horizon MDPs, which basically, as you are computing the optimal value, you are computing the policy. Because basically, you have B0, and let's say this is S1, S2, S3, S4, and let's say you're computing S2's B1, which is one step to go value. Okay, then suppose I just make up some numbers. This is the B0 would be just the rewards. Imagine the rewards are like this: 1, 2, 3, and 4. I just make that. Okay, and suppose S2 has just 2 actions. One action is black, which basically is 0.7 goes here and 0.3 goes here. Okay, and then it also has another action, this red action, which with 0.9 goes here and 0.1 goes there. Okay, now what does that mean? So basically, if you have 0 steps to go, this is just what I did in that the example that I recorded for you guys. But if you have 0 steps to go, then the value of that state is just the reward because you don't get any more. Okay, if you have 1 step to go, the value of this state, this guy gets to decide, should I do the black action or the red action? Okay, if it were to do the black action, it will get 0.7. We'll get 0.7 times 1 plus 0.3 times 3. right? 0.7 times 1 and 0.3 times 3. Okay. Whereas if I were to do the red action, I get 0.9 times 2 plus 0.1 times 4. Okay, so here I have a choice. The state has a choice which way. You know, when the agent is at that state and has one epoch to live, it has a choice which action would it rather do. It would do the action that gives it the maximum value. Okay, and so basically, let's see which one is bigger now. 0.7 times 1, that's 0.7, plus 0.3 times 3, that's 0.9, right? And that would be 1.6 here, and this is 1.8 plus 0.4. This is 2.2. Okay, so this is 2.2, that's 1.6, so it will take the red action. Okay, and when it takes the red action, notice you can just remember I took the red action. That means the policy here is red. That's the action to do. So in doing optimization of the value, you already figured out what action to do. Now, of course, the next question is, what is the value of S2? Value of S2 is whatever you are getting from this size 2.2 plus the reward of S2. What is the reward of S2? It doesn't change. It's the same as before. It's 2. Okay, so then this becomes 4.2. So in essence, when you're doing the finite horizon MDP, there really is no distinction between computing the policy versus computing the value. You're computing the value, and when you're computing the value, you just get the policy as a byproduct. Yeah. Whereas in the infinite horizon, that's not the case, and so that's why you actually convert value into policy and vice versa. Are there going to be any other sample exams posted? Didn't you get enough? There are lots and lots of questions out there already. Okay. Any other questions? I saw that I just saw that one from 2012, right? I don't know. Also, that exam, yes, was in 2012. Yes, go ahead.
For the homework 1 test, on question 4, it's like a series of functions that the optimal path boundary uniform search uses.
Mm-hmm.
I don't know. Can you explain that?
I need to look at what that question is. I don't know what it is.
Yeah, the homework 1 test.
It's the, if you in the uniform cost search, if you are adding a constant, if you are multiplying it by a constant, the cost that you
Is this 4 updated graph search?
Yeah, it's the cost between things I and J in a graph
Wait, I mean, are you talking about question number 4?
in the test for homework 1.
I know, yeah, homework 1 page. Are you talking about question 4?
Yeah.
Question 4. This question we added line 14.
No, that's the 3D search. You're talking about the transform action cost, right?
Yeah.
Yeah, so that must be the question this step out.
Yeah, it's
Oh,
it's
okay.
above the updated graph.
Oh, so you're updating. You're updating.
Like a constant.
Yeah. So you are just basically, you are trying to look for affine transformation, the only thing that changes, that leaves. So yeah, this is sort of an involved question. An involved question. So you just have to, you guys all should have to hope that Sharad doesn't set the exam. So I mean, in essence, what they basically came up with. So what were you looking for? You were basically looking for the fact that only affine transformation.
Yes, right. So we were trying to see if this thing, like, if this thing holds, they should be able to do. As like the transformation should not reduce.
The optimality.
Yeah.
Okay. Well, there is a square. Oh, square can reduce if you have less than 1. Yeah. So this is basically linear versus nonlinear transformation of the class. Okay, and it's a very involved question, and involved with respect to maybe some of the other simpler questions. And affine transformation, that means if you add or if you multiply cos by a constant and add a number, then optimal path on that would be the same as optimal path is before. Okay, but any nonlinear transformation you're not guaranteed. And to be able to say you're not guaranteed, I just need to show you one example where, you know, the cost with the square path. For example, take square path. Okay, the square path, actually you think squares should be monotonically increasing, but when the costs are less than 1, the squares are reducing, and that's enough for me to come up with a situation where the optimal path would be different. Okay. An interesting related question.
You can also take example 1114 times and 3 only one time. So it will be 9, it will be 1114.
That's true too. Yeah. So multiple ways nonlinear transformations change which is the minimum sum, because you're summing up the cost values, and if you're squaring and then summing up, you know, then you're not going to have. So in general, you have to ask yourself, essentially, you had A1, suppose you had A1 plus A2 plus A3, which is the original path, and it was obviously less than some other path, A1 dash plus, just a simple way of thinking about it, A3 dash. Okay. Now, if this is the case, and then I give you a transformation, saying, if this is the case, would A1 square plus A2 square plus A3 square will still be less than A1 dash square plus A2 dash square plus A3 dash square. That's not guaranteed. Okay, because if it's not, then this path is no longer actually greater than this path, so this should have been the optimal path. Okay, whereas if on the other hand you are doing CA1 plus B as the transformation, okay, then CA1 plus B and CA2 plus B plus CA3 plus B, this can be shown to be less than this. With the same transformation, CA1 dash plus B plus CA2 dash plus B plus C, as long as C is positive. If it's negative, then you're in trouble.
For this question, you're just looking at linear transformations.
It's, yeah, linear transformations don't change the ordering. Okay. There is a more interesting question though, which is a related question with respect to min-max and expected max. Okay. Min-max, if I essentially, all that matters in min-max is the actual ordinality. That means which numbers are bigger than which numbers. If you keep the relative ordering same, then the top level move that you pick are going to be the same. So that's notion of ordinality. Okay. Whereas for expected max, because you know basically you're actually summing them, you know, you're taking the expectations and then you're picking, you know, then you're taking the max. It's no longer guaranteed. So in the expected max, the actual cost numbers matter. This matters because all costs are essentially going to be estimated. Because in a real game, you don't know the true cost, so you may be estimating them. So you probably, instead of estimating the considering the A1, you may have basically did a linear transformation, and that's what you got, and that could be quite different. Okay. So in this case, actually, linear transformation works, but even affine transformation doesn't work for these are called affine transformations, and even those don't work for expected max. but they will work for many
And
years.
linear also has a limitation that you can't add negatives.
That's what I'm saying. There are no negatives. In fact, yeah, I add even multiply by negative numbers. You multiply by negative numbers, you just change the order. Yeah, that homework quiz, I think it was only sent to people who had done extremely well in the homework one in class. So I won't say anything about that. Other questions? Okay, no more questions. Are we expected to write code for the exam? Of course. No code, no code. What? No code? No, I don't need code necessarily. There's also a video explanation of the simple exam, sample exam. Yes, I did do that. I walked you through the problems. Yeah. No, I know that you already done the projects for all these things. So I'm not basically, that part is understood. So in some sense, I'm much more interested in seeing whether you understand qualitative connections. And that's sort of important to me too. That's what I spend a lot of time in the class, as you can see. Anybody, I mean, in my view, plug and chug is easy. You read an algorithm, you put the numbers and plug and chug is easy. Figuring out which algorithm corresponds to which. For example, something like greedy best first versus hill climbing. You'd be surprised. I would not be off the mark and saying that world over, probably 60, 70, 80% of the people don't know the difference, having completed microBI class. Because they look almost similar. They both have the same problems. They both actually fail to find the optimal solution. But but they have very, very different properties beyond that, because greedy best first basically is still systematic and hill climbing isn't. And so I think, in fact, in the class, I mentioned this idea that hill climbing essentially has no commitments. So it just, something looks interesting, it can just commit to that. Okay. Whereas if you have a search tree, then you have to follow the search tree. You can't just randomly shift to somewhere else. And that reduces what they call the freedom of mobility in the search space. And hill climbing can just follow the local gradients. And which can be good, which can be bad. And the other guy doesn't follow the local gradients. It's constrained by the tree, which can be good, which can be bad. And so it's figuring out those trade-offs. No questions on alphabet open? No questions on game trees? I'm trying to figure out what questions to put on the exams. The ones that aren't asked are the ones. This is actually intelligence gathering. This is how to set the exam.
Exploration.
Yeah, I'm going to exploit you guys. That's the truth of this. Which is the from what question?
I haven't watched the previous video yet, so I don't want to ask a repeat question.
No, you can ask a question. That's fine. If I answer, it doesn't matter. Review session may have various things. What's the question?
So I'm like, there's like a specific question.
Yeah. Okay. Where was that? I think it was Where is it? Where is it?
It's just last.
Oh. No. So is there a specific way of finding? In fact, I don't know. I must have probably mentioned this yesterday. I don't know. Yeah. In general, finding the representation is an art. Okay. Finding the best representations is still an open problem, honestly. So one of the interesting quote unquote claims made by deep learning folks, which we'll talk a little bit about later, is they are learning representations. And if you ask them what representations they learned, they basically will say whatever is in the intermediate nodes is the representation we learned. But in general, given a problem, you can write it in multiple different formulations. And which is the best formulation? There is no algorithm for computing. Okay. So, but you could do very bad representations. For example, I mean, you can essentially, as I said, now I remember, I made this whole thing yesterday about minimum versus minimal. Okay. Minimal essentially means you came up with a representation. I can, in front of you, remove one of the state variables and will still have all the information. Then I know that you are unnecessarily verbose. Okay. A minimum, on the other hand, basically says globally there is, some other representation that has fewer state variables. Okay. And furthermore, actually, having the least number of state variables is not guaranteed. In fact, what is the badge we are trying to get in coming up with a representation? That representation should help reasoning and should help learning. Those are the things that you really care about. And it turns out that having the minimum number of representations, minimum number of state variables don't necessarily guarantee that at all. Okay. So in general, finding representation is not, I mean, we were not checking to see whether you know the algorithm for coming up with representation. It was more of, you have an approximate idea and you come up with very bad redundant representations. That's about it. Just one more. Non-exam question. Is there any way project 2 can be extended actually? Why am I supposed to answer this now? Yeah, I did not see it. Right. I can't stop this. I always want to extend, but it's the TAs who don't allow. It's the other TA that's not here.
Here, then you could just.
But it's not me. They are deciding, They may want to go somewhere. Yeah. Is it true that the final is take home? Well, I have no idea. I normally, if I trust the class, I will do everything take home. I don't yet trust the class right now. So I don't know that I can trust you guys. So if I trust you guys by the final, especially if there's only one person left and I trust them. But seriously, I mean, I do believe that take homes are actually very reasonable exams, and I do it a lot of times, but I also don't do it sometimes. I mean, this is unfortunately collective justice. I can't necessarily say for some of you it is take home and for some of you it's not take home. So for example, it turns out that for homework 1, we didn't make a huge federal case on this, but we have our reasons to suspect that some people did actually get the solutions that were posted by mistake and were able to essentially, use the answers. And that was another reason why the quiz was sent, between all of us. So I want to get out of that. I want to get to a point where I more or less trust. Or I think that the people who aren't trustworthy aren't doing well anyway in the class, in which case it doesn't matter. So that's typically, I actually like take home so that I can teach more and not waste less time. But there's no answer right now that I can. Can we expect questions on worst case scenarios for search algorithms? I don't know. I will start thinking about it. Yeah, possibly. Yeah. So this fall grade coming up?
Yes.
When?
This
This
Monday,
weekend,
Tuesday,
Monday,
this Monday, Tuesday, Thursday.
Tuesday.
This Monday and
You
Tuesday.
just made this up. I didn't know this. Oh no. Okay.
Should extend the project.
Extend meaning make more. More questions.
The deadline, like.
Okay. Well, we'll take it into advisement. Then you will know. We'll change the thing. Any other questions?
You know, you guys can finish it with some work. You don't have to worry about colleagues doing work and just finish it with other things.
Now the other problem is we are falling behind the graduate AI class.
Oh, yeah.
So we can't let the graduate AI class win. What? That's what I'm saying. See, so we can't let graduate AI class take over the badges. No, I understand your concerns, and we'll talk. I'll talk to the DAs and let you know. Okay.
Didn't we go over question 7 for the homework?
I don't know.
That was the last time. We left the tax.
Homework 2 and question.
Evaluation.
This one. So
Yeah,
this one.
yeah. So it's just they have to build the tree for each step and see if the action would take them the best. You don't get the best value.
How do you build?
You actually have to do it.
No, so you don't ask how do I build the tree because that's extremely easy. Okay, because seriously, I mean, again, I think the point is, I'm not trying to put you in a spot. I mean, building min-max tree doesn't require you to know what would be the evaluation function. Min-max tree, all it is saying is, I am starting from a game position and I'm considering, so basically, and I'm considering all the moves I can make. And you should know, that's just knowing the game. Okay? And for each of the moves I made, all the moves my opponent can make. Okay? That's just game logic. It has nothing to do with which board is good, which board is bad. So you should be able to expand the min-max search tree to any depth. The interesting question is, if you stop at a particular depth, and you apply this, I guess, the evaluation functions they have given, and then you do min-max over the tree, then are you getting the same action back up? Is basically what that question is asking. Okay.
The same. Second part.
That is question 8, you mean?
Second question, the one with player 1 action 1 action. This one.
Oh, this one, you want that, yes. So what happened there? Oh, can you get rid of, so what's your question there? Now I can see this.
Part 2, so part 2. I even posted on the other, but I didn't get it. Assume player 2 chooses action at random at
Oh,
each.
he's talking about 50 max, yes. That's the
I got how to calculate expected max, but the question says for what values of x is player 1 guaranteed to choose action 1. But it can guarantee to choose action 1.
No, guaranteed means it's whichever basically, I mean, so why can't you guarantee? I don't know.
In this particular problem, it's not guaranteed he will choose action 1. After using that, because he can choose action 2 also, no? Because he would just want to maximize its value. So in some cases, the maximum value is coming on action 2. So how can I guarantee it's exactly action 1?
I don't see. If you set x as a particular value, right? You have x greater than something. Yeah. So you have a calculated expecting max part of that. So what is the value you got to get for that? Solutions. They have solved it.
Yeah,
It's x greater than 9.
yeah.
Right.
was saying that in the question is that player 2 chooses from random, right? But player 1 knows.
The goal state is
player
at
one
one
choose
of
level,
the
right?
extreme end of it.
It's going to
Okay,
from
can you
there,
guys, okay, why don't you talk to him after that? Okay, let's just, there were some other questions, and then once we disband from here, then we'll do that. So there's another question here saying, oh, so the worst case scenarios of if there is goal state at the extreme end of the leaf level, which search algorithm guarantees optimal performance? Well, that looks like an interesting question. I could ask. I mean, the questions of the type, let's see, there. Oh, this one, yeah. Yeah, so the short answer questions basically can be capturing these kinds of things. I'm not saying I have a question on that, but I think that again, I mean, we should be able to think about. So I think it's good if you are thinking about those sort of worst case performance issues. See, I understand that all of you are interested in your grade. I'm only interested. I'm only interested in seeing how far you can think. And in the end, I can assure you that your life during the semester might be sort of unhappy, but your GPA is not going to be worse because of this course if you take the course. That's just the way it is. So I would rather deal with separate those out and make people try to learn as much as they can, and then give some grades there. And nobody typically ever complains. So I'm not saying this is Christmas, so that's not the issue. So don't compare yourself to other classes where you might say above 90 is A minus sort of a thing. I mean, many times when we have nobody above 80, and that's okay. I think we did have last year. So you should leave that part out. And I would essentially set two kinds of questions on the exam. One, to kind of see, are you even paying attention? Do you have some sense of what's going on? And then the other is, do you go at least one or two steps beyond what I'm mentioning in the class? And those are two different pieces. Typically, the short answer questions would be of the second type. Because I'm basically trying to mess with your minds. Does heuristic have an effect on space complexity of A star and IDA star? That's a very good question. IDA star space complexity doesn't have any, I mean, so you can answer this actually. Does any of you want to answer? There's a question as to whether the heuristic affects the space complexity of A star or IDA star.
A star it surely affects, right? Because like if let's consider that a reducible heuristic, you take the example. So when I am at the even level, I will be considering all the odd levels in that next, right?
There's a much simpler way to say that. H equal to 0.
Yeah, H equal to 0.
H equal to 0 across the board. A star becomes uniform class search. Uniform class search is breadth first search. Breadth first search is the original sin in space efficient search because it's going to take before the space. Okay, so A star, depending on the heuristic, can take humongous amount of space. Okay, the question about IDA star is much more interesting.
IDA star can actually take more time to solve depending on the heuristic, but space will not be because it's gonna use depth first search. So my answer.
That's correct. That's correct, because IDA star will just use depth first search, and depth first search just uses B times T. Okay, whereas branching factor times depth as the maximum space it ever uses. So IDA star's problem is not so much that it uses too high an amount of space, but oftentimes it's not using all the space that is actually available. Okay, so you don't get any, you die if you need one more byte than is available, but you don't get any badge because you actually did not use all the memory. Okay, so in fact, it makes sense to maximally use all the memory. And that's where there are algorithms, which we didn't talk about in the class, but there is SMA star and there is recursive best first search, which basically do a better job of using all the memory that is available. And in essence, what they'll wind up doing is they'll fill up the memory. And then when a new guy has to be put in, I mean, ultimately filling up the memory is about open list. Open list becomes larger and larger. Of course, if you have graphs, then it's also closed list. But when the list is become too large, then somebody has to be thrown out. Okay, and when they're throwing it out, then essentially they will keep enough information such that they can reconstruct the guys who got thrown out. So it's some sort of a paging strategy, the same kind of thing that the operating systems use. If you have a page memory, keeping it completely clean and just having 1 or 2 pages in the RAM doesn't get you any efficiency. So you want to actually put as many things. In fact, that's basically what most of your programs these days do. They prefetch and put everything in the RAM. And then, of course, if something else wants to come in, then you need to throw somebody out. And so the one thing that we didn't talk about, which SMA star, etc. do, is how do you throw nodes out to make space for the new nodes that are coming in. And if you do that, then you will use all the memory, and then you can actually do much better than IDA star. IDA star is a pretty bad algorithm, actually. It's like a nice thing to talk about, but it's really bad. In terms of time, in terms of time, because you're doing, as we said, basically, if you have unique heuristic values, you die. Okay. Yeah, in the very beginning of the review session, we had a whole discussion on greedy best first search. Okay, so Habib, you should just, when we're done, basically look at the recording and then just go to the beginning. There's an entire discussion of greedy best first search and connection to it. Anything else? Okay, thank you. Anybody else has any other questions?
So you calculated it
Just as a note regarding the
So here,
here we see RN correct selected. So what is that? Here either it can be 12.
no, that's the point. Expecting max, you don't randomly choose one. You take the expectation. This 0.5 probability is
But think about the natural case scenario.
no, this is yes, the expecting max, you don't randomly choose one. You take the expectation of it. So it's 12 into 0.5 plus 8 into 0.5. But that is not good.
I can in the practical scenario, it comes like the probability is selecting of both is half, but at the end it's realized it comes like one, right?
So this is how expecting max can give us. I cannot. That's you can only talk about expectations. Right?
So I was actually.
So the question was decided to starting point. I don't know. Yeah, but I can
But actually, if I can finally, right, in the real case scenario,
I will send you.
you can't say that there is one
Does cheat sheets help? Why do people like cheat sheets?
generate perception of some, not everybody.
So how does it help?
I don't, maybe they could write down the value.
Actually, I did find that some people will do extremely well. They spend a lot of time writing the smallest, font possible. Actually, somebody has done this in printing.
Oh, wow.
So maybe if I allow cheat sheets, we will say it should be handwritten. So then you should be able to read, micro miniature. It doesn't really matter. If you write all that stuff, you have to read it.
What? The question is, can you bring a teaching? So,
That's why I'll send a mail on that. Somebody asked a question, I chose not to answer, but now I have to answer and I go back.
But I don't think it is required. This.
It's never required, of course not. But
Because there is no like formulas in this subject. Some subject has a long formula that might be like.
So, Professor Ab, the Prashant's question was like this homework was designed in such a way that the value we get from minimization is the expectation. So, like we use expecting max to do expectation. His question is what happens in worst case? So, in worst case, he is saying like if it is a random agent, and it just selects like the best possible. Well,
no. Expect max agent, you have to give probabilities that will get you what you want.
But in real life, like
No. Listen. This business of real life is a whole entire issue. This problem, if it says expected max, you should be able to give probability distribution, a single probability distribution with respect to which you will be that. Okay, you can't just say I won't have a probability. I will just because that's like saying I know like basically So what you are saying is I know what outcome I want when I am throwing the dice. So in real life I can want that outcome. No, you can't want that outcome.
But that outcome can come in some case scenario, right? Well, if I wrote it 100 times or like 1,000 times.
No, but I mean, my point is, it's based on expectation, right? Okay, that's I can see where you're getting stuck. In the game, that can happen. They're not doing the game, they're thinking right now. And they're thinking right now, they can't just assume that the best thing will happen or the worst thing will happen. If they're expecting max agent, they have probabilities and with respect
So it's
to
only
which-
happening in the model.
Exactly. The entire min-max search is in the head.
I understand that.
Yeah.
But how we can the thing which is confusing is guarantee. There is no guarantee in using action one. But in modeling,
No, I think the question is, can you provide probability such that min-max algorithm will guarantee? That's all the question is. And you are saying, in fact, one of the other interesting things is you may choose, min-max analysis might tell you an action, but you may choose not to do it anyway.
Anyway.
Right? That's a different story. In fact, that's the whole point about much of anything that you do in your
So
head.
we can even get better value than expecting max.
Of course. I mean, just like honesty is the best policy is not actually true, because sometimes when you're honest, you lose money. Right? So specific times, so it's all probabilistic. If you do it enough number of times, speeding is a bad policy. If you do it enough number of times, the tickets you get outweigh the minutes that you cut down. But there will always be, you can always show a particular time when you just speed it and you'll find it. So it's a question of, is there a consistent probability distribution, including 0, 1? You can't just change the distribution. You can't say, I look at what I'm about to get and say, I like that, so I'll change the probability distribution. That's not expectations. Okay?
If we talk about the model thing, like in virtual thing, yeah, it makes sense.
But I mean, the entire min-max is virtual.
Virtual thing.
Yeah, because, but I mean,
yeah.
what else would you do? I mean, the whole point of min-max is thinking in the head.
Yeah, I
In fact, so you assume, so this is part of the reason why we pointed out that if you do min-max, you play chess with your 2-year-old niece or nephew, people will laugh at you. Because they are likely to be eating the pieces, and you are thinking very carefully about what's the best optimal action.
Minimax is what you would surely do. I mean, there are other
No,
algorithms.
min-max is basically guaranteed. So there are two definitions. Min-max guarantees that it reduces the probability of losses. It's like that. So it tries
You
to
can't
make
do
sure.
worse than this. Minimax actually assures that, right? We can't do worse than this.
No, you can't do worse than min-max. No. All min-max is saying is ensuring, okay, we should probably just stop this one.